All right, so today's topic is still about probability, but a new type, I guess, called conditional probability. Okay, so you guys know the word condition, like it's a requirement that must be met for something to happen. Okay, so let's look at this situation together. An ice cream shop sells ice cream, of course. So they only have two flavors of actual ice cream, chocolate or vanilla. But then whatever flavor of ice cream, it can be served in either a cone or a cup. Okay, so let's say they sold 250 total ice creams one day, 170 cones and 150 chocolate. There were 70 vanilla cones. Okay, so let's go ahead and make the table together so that we all have the same thing. Remember, a two-way table, you are sorting the data based on two different factors. So here the factors are the flavor of ice cream and I guess like the container, whether it's a cone or a cup. Okay, so I'm just gonna put chocolate and vanilla across the top. And remember, we always want to put a total column. Okay, so then down the left side, the other way we are grouping them is by whether they got a cone or a cup. Okay, so now that we all have the same setup, go ahead and take a minute and see if you can fill in the table using the numbers from the problem. So let's see, there's 250 ice cream. So there's no mention of flavor or cup versus cone, so that must be the total. So that goes down here. Okay, they sold 170 cones. So again, that doesn't say anything about flavor. So those are the total cones. And 150 chocolate. Okay, so again, nothing about cup or cone. So the 150 is the total number of chocolates. There were 70 vanilla cones. Okay, so that would be both vanilla and cone. Okay, so those are the numbers from the problem. And then now we can fill in the rest. So I'll start over here. 170 minus 70. The other 100 cones must have been chocolate. Out of the chocolate ice creams, 150 total, 100 were in cones, so the rest were in cups. 150 minus 100 would be 50. I'll go over here next. 250 total ice creams, 150 were chocolate, so that means that the other 100 were vanilla. Okay, here 100 total vanillas, 70 were cones, so the rest were in cups. 100 minus 70 would be 30. Okay, and then you can either subtract or add. So 30 chocolate cups plus 30 vanilla cups means a total of 80 cups overall. Okay. So with that in mind, we're going to do a couple different things with it today. Okay, so lightly shade the data that shows the amount of cones sold in the day. Okay, so this entire row is about cones. Right, this tells us chocolate cones, vanilla cones, and then total cones, right? So all of that is info about the cone. Okay, and then next instruction, circle the data that shows the amount of chocolate ice cream in cones. Okay, so not total chocolate, chocolate in cones, right? So that would just be this one. Okay, so next, bringing back probability. What's the probability that a random person got chocolate ice cream in a cone? Okay, so there's two requirements, right? They not only needed to get the flavor of chocolate, they needed to get it served in a cone. Okay, so remember, we can express probabilities using notation, probability, and then parentheses. Okay, so probably I'll just say chocolate in cone. Okay, so probability we learned is number of successful outcomes over the number of total outcomes. So I always like to start with the denominator. So what's the total number of things that can happen when I take a random person? I can talk to any of the 250 people, right? So that's my denominator. Okay, and now of those 250 people, how many are considered a success? And again, right now, I want them to not only have gotten chocolate ice cream, but served in a cone. That would be the circled number, right? 100 people fit the exact description of getting chocolate in a cone. Okay, and like always, we could reduce this fraction to make the number smaller. Okay, so now we're gonna introduce a new type of probability. Okay, sometimes you have a partial piece of information about the situation. Okay, so let's say that the person you talk to, you see them as they're throwing away like the wrapper to their coat. Okay, so you know for sure they got a cone, but they already, ate up all the ice cream, so you can't see what flavor it was, but you know that they got a cone. Okay, so what's the probability that this person got chocolate ice cream? Okay, so the denominator is no longer going to be 250 because not all 250 people got a cone, right? So there's only 170 possible people that had a cone. Okay, so the denominator is going to be different. Right? Because I'm not allowed to talk to all 250 people anymore. I can only talk to the 170 people who got a cone. Okay, so out of those 170 people, how many of them met the success criteria of chocolate ice cream? Still 100 of them. Okay, so 100 out of 170, which reduces to 10 over 17. Okay, so this sentence that you know for sure they got a cone, but you want to know if they got chocolate. This is the new notation we use. Okay, so probability of. And so the first thing is the success criteria. Then you have this vertical bar. And then afterwards is what's called the given, the thing that you know happened for sure. Okay, so let's write below. So in general, right? So the first word, the first thing in the parentheses is what's considered a success, then the vertical bar, and then what's afterwards is what's called the given. Okay, so given means that this happened for sure. Right, normally with probability, you are just calculating the chance. You don't know if it happened or not. With this thing called conditional probability, the thing after the vertical bar, that's called the given because it's guaranteed that it happened. Okay, and so you would say this out loud as what is the probability of chocolate given cone? Okay, so looking over here now. So here we have a different thing. I don't want to say it out loud because it would give a little bit away. Okay, so why don't you go ahead and see if you can write in a sentence what exactly this means, and then go ahead and calculate the numerical value. Okay, so yeah, go and take a minute and see if you can do part 5, please. Okay, so you may have noticed, well, it's the same two words, chocolate and cone, but this time the word cone comes first in the parentheses, and then after the bar is the chocolate. Okay, so that does switch what's considered a success and what's the given. Okay, so this time the chocolate part is given. Okay, so you know for sure that the person you're talking to got chocolate ice cream, right? Maybe they like have a smudge of chocolate ice cream on their cheek, or they like got a stain on their shirt or something, right? So you don't see whether they got a cup or a cone, but you can see clearly that they got chocolate ice cream. Okay, so I'm going to write it in a sentence. So given you're talking to someone who got chocolate, what's the probability they got a cup? Right, so this time you're not allowed to talk to anyone who got vanilla ice cream, right? Because you know for sure the person got chocolate ice cream, so you're only considering those people. Okay, so the numerical value of this. Okay, so again, you're only allowed to talk to people who got chocolate ice cream because you know that's true for sure. Right, so for the purposes of this problem, I'm going to temporarily say, like, right, you would throw all of this data away, right? You don't care about the people who got vanilla ice cream. You don't care about the total because those include people with vanilla ice cream, right? The only numbers you care about are the people who got chocolate ice cream. Okay, so of those people, there's only 150 people you're allowed to talk to. Again, you're not considering any of the people who got vanilla ice cream. So the denominator is now 150. There's only 150 people who fit the requirement of getting chocolate. Okay, now of those 150 people, we're considering it a success if they got a cone. Okay, so there are 100 people who got a cone. Okay, so 100 out of 150, which reduces to 2 out of 3. Okay, so we notice that the two conditional probabilities, right, even though it's the same two words, they lead to different answers, right? 100 out of 170 versus 100 out of 150. Here, it's probably better to look at the unreduced fractions rather than the reduced one. Right, so you see the numerator is the same, right? The 100 represents both chocolate and cone. So whichever piece of information you're given, it fits the other one also, right? But what's different is the denominator. Okay, and again, the denominator comes from what is given. When you were given for sure they got a cone, you could only talk to the 170 people who got a cone. So 170 was your denominator. When the given was chocolate, you were only allowed to talk to the 150 people who got chocolate. Okay, so the given is different, and that's what controls the denominator. Okay, so yeah, order definitely matters with conditional probability. Okay, so you want to know that the given is how you determine the denominator of your probability fraction. Okay, so I want you to practice using these new conditional probability symbols and calculations. Okay, so I want you to come up with two of your own. So you can't reuse the ones we've already done. Okay, but yeah, using the info above, first give me like a sentence about what you're asking, and then give me the symbols and then the actual fraction as well. Okay, so please take a few minutes and try to do both or the entire rest of this section. Again, your answers may not match mine. They can still be correct. If you're not sure if yours is correct, I'd be happy to look it over afterwards. Okay, but let's say that you want to do if someone got vanilla, what's the chance they got a cup? Okay, so here I know for sure they got vanilla. So that would be the given after the bar. And the thing I'm not sure about, the success criteria, is if they got a cup. Okay, so for me, the given is that they got vanilla. So the denominator, I'm only allowed to talk to the 100 people who got vanilla. And of those 100 people, 70, oh no, sorry, this time I want a cup, right? So 30 got a cup. Okay, and then one more. Okay, so let's say this time I know that like given someone got a cone, what's the probability they got vanilla? Okay, so this time I know for sure they got a cone, so that goes after the bar. What I'm not sure about is whether they got vanilla. Okay, so the denominator comes from the given, so I'm only allowed to talk to people who got cones. So I can talk to any of the 170 people who got a cone. Of those 170 people, 70 got vanilla. Okay, so again, it's likely that you pick something different than me, but that's the idea. Okay, so questions on anything here? Okay, so moving on to the back then. Okay, so here's another situation. Experiment was testing how many adults and children had chickenpox. Of the 300 adults, 50 had chickenpox. Of the 200 children, 30 had chickenpox. Okay, so yeah, the two ways we're classifying the people are by age, so whether they're adults or children, and then whether they, yes, have had chickenpox or no, they have not. Okay, so I'm gonna give you guys a few minutes to try the whole scenario. Okay, so make a table first and then use it to try problems 8 through 11. Okay, so give it a try. And if you weren't sure if any of your conditional statements on the front page were correct, feel free to raise your hand. I'd be happy to take a look. Just remember your table may look different than mine because you could put the children and adult this way, or you could put them this way. You could put the children first, you could put the adults first. So the way I'll do it is I'll go children and adults. Okay, and then the other criteria is whether they've had the chicken pox or not. Okay, so I saw some of you said like yes and no. Some of you said chicken pox and no chicken pox. Yeah, there's different ways you could have phrased this. Yeah, I'll go chicken pox and no chicken pox, I guess. Okay, I guess I should say child. Okay, so let's see. 300 adults. Out of those 300, 50 had chickenpox. Out of the 200 children, 30 had chickenpox. Okay, that's all they give us, but that's enough. I'll start by going this way. 200 children plus 300 adults means 500 total people. 30 children plus with chickenpox plus 50 adults with chickenpox means 80 total. Over here, 200 total children, 30 had chickenpox, so the other 170 didn't. 300 minus 50 is 250, and then 500 minus 80 would be 420. Okay, so probability of an adult given chickenpox. Okay, so again, you can phrase this differently, but I'll say if someone has had chickenpox, what is the chance, the probability, the likelihood they are an adult? Okay, and then the actual numbers. The denominator, you're only talking to someone you know for sure has chickenpox, so 80. Okay, so you ignore the rest of the table for now, right? You only focus on the 80 people with chickenpox. Of those 80 people, 50 are adults. Okay, so 50 over 80, which reduces to 5 over 8. Okay, probability of chickenpox given child. Okay, so here you know for sure you're talking to a child. Okay, so the given is that they're a child, so you're ignoring everything except the children. So 200 total children you could be talking to. Of those 200 children, 30 have chicken or have had chickenpox. Okay, and that one we could reduce to 3 over 20. Here, I asked you to come up with a probability that is equal to 3/8. Okay, so you're looking for something that reduces to 3/8. So 30 out of 80 would do it. Okay, so that means the given needs to be the chickenpox. And the success needs to be child. Right, because again, that would be 80 as the given denominator. So 30 over 80 reduces to 3/8. Okay, and how about 1/6? 50 over 300 would reduce to 1/6. So the given needs to be adult. And the 50 is from having chickenpox. Okay, let me just write out. Okay, this is 50 over 300, which reduces to 1/6. This one was 30 over 80, which reduces to 3/8. Okay, so questions on any of this? Okay, so lastly, let's tie it back to the standard deck of playing cards. Okay, so here's the full set of images again. So just a reminder, right? Clubs, spades, diamonds, hearts. Both of these are black suits. These are red. Right? The A is for ace, J for jack, Q for queen, K for king. Okay, so here I just you're drawing a card randomly, right? The cards are face down, so you don't know which one you're going to get. Okay, these are all separate problems, so don't worry about like, oh, do I shuffle the card back in? Each problem, you're starting from the full 52 card deck. Okay, so make sure you look carefully. A lot of these are on purpose very similar to each other. Some may be the same, some may be different. Okay, so go ahead and take a few minutes and see if you can answer these six probability statements. Okay, so for ace, probability of ace given black. Okay, so you are only allowed to pick from the black cards. So there's 26 black cards to choose from. So even though there's 4 aces in the original deck, remember, you're not allowed to choose the red aces. So there's only 2 aces in the black color. Okay, so 2 out of 26 reduces to 1/13. Okay, next, probability of black given ace. So this time ace is the given. Okay, so here you're throwing away almost the entire deck. You're only left with the 4 aces. Okay, so that's your denominator. Of those 4 aces, 2 of them are the black suit, or a black suit. Okay, so 2 out of 4 reduces to 1 out of 2. Okay, by the way, yeah, some people did like 26 over 4 because they said, oh, there's 26 black cards. For the full deck, that's true, but remember, you threw away all of these cards for this problem, right? So only 2 black cards remain. And also, probability can never be an improper fraction because the denominator is total. So you can't have more than the total. Okay, 3, probability of a black ace. So here, there's no condition. There's no bar. So you're drawing from all 52 cards again. Of those 52 cards, 2 are both black and ace. Okay, that reduces to 1 out of 26. Problem 4, probability of club given black. Okay, so just like the first problem, you're throwing away all of these. So there's 26 black cards to choose from. Of those 26 cards, 13 are clubs. Okay, so 13 out of 26 reduces to 1/2. Next, just probability of club. No condition, so all 52 cards to choose from. So 13 of the 52 cards are clubs. Okay, and then lastly, probability of club given ace. Okay, so given ace means, again, you throw away every card that's not an ace. So you only have 4 options to choose from. Of those 4 options, one of them has the suit of clubs. Okay, so 1/4.